We're going to get going with the second talk of today. Our speaker is going to be Prabhakar Raghavan. Many of you might know him as the co-author of two wonderful graduate texts in algorithm design. In fact, I studied algorithms back in the day from the randomized algorithms text. But he also wrote this book called Introduction to Information Retrieval that some of you might be familiar with. Prabhakar has done a lot of fundamental work on the, on web search, on databases. He's currently the chief technologist at Google, and I guess till very recently he used to work on search at Google. And these days he has gotten very interested in the use of AI and like specific tools, specific AI tools in proving theorems in theoretical computer science. And he's joining us all the way from Indonesia to tell us about these exciting new developments. So Prabhakar, please take it away.
Hey, thanks, and good morning, everyone. First, my deepest apologies for not being there in person for what seems like an amazing workshop. I'm really sorry not to be there, but somehow I managed to double book myself, be both in Utah and Indonesia. So I had long that trip, so my apologies. I want to talk to you today about some of what I already worked in LLM-assisted Math and Theory and what we're learning in the process. So this is part of a journey that I expect to go on for a long time with lots of amazing breakthroughs. So this workshop's very handy. The work in, the technical results I'm talking to you today are a joint work with Ansh and Abhijit Prabhakar. Ansh is a graduate, or was a graduate student working here. Abhijit is a research scientist at DeepMind. Next slide, please. Okay, so I come to this question of what do we have from a particular perspective? I'm not asking, was AI used to have prove something here, solve some math problem? The answer to that is a resounding yes, and you'll hear many examples today and elsewhere about this. The thing I'm really interested in is how can AI help math and CS research in ways that humans cannot? And this is a bit of a difficult to define question, but there, as we try to get to it. And my curiosity was piqued some months ago by this paper by Tony Feigen and Company, when they looked at a range of so-called ethics problems and managed to solve, improve on a bunch of them. But then they had this very beautifully honest remark that said, our findings suggest that the open status of the problems they track can be attributed to obscurity rather than difficulty. So in some sense, you want to get past the obscurity boundary to the really difficult problems. Next, please. So then you have this recent manuscript that some of you are familiar with. I think consider this a fairly major breakthrough in theory, where that biparty matching, which was known to be RNC, is now an NC. And if you look at this manuscript, the authors acknowledge that AI played a somewhat material role in the entire solution. Now, the credit goes to the humans in this case. They did much of the work, but they do point to AI as having one of the key insights that it looked at. Now, there's something nice about this. This is a major problem that Flux Smart from the people looked at, but at the same time, it still doesn't have this notion of the AI in it all. And then next week's, you have obviously this landmark result from OpenAI on unit explore one event one data. And when I look at this, it has many of all the right ingredients. It's a hard problem, and known to be hard from lots of human study. It was a case where a model given a prompt essentially without further interaction went off and discovered the result. And there's something nice about this prompt, and it's off the spirit of the kinds of things that I'm especially excited about. Next, please. When I look at the landscape of AI-assisted math and theory today, I think of at least three tracks. So the first track consists of building tools, including retraining models, fine-tuning the math code, and other AI harnesses that they sometimes call in pursuit of proving theorems. And I'll talk to you a little bit about one of these today. The second track has to do with using these tools to really do the job we want, which is to crack our theorems. And then the final track has to do with understanding the capabilities and limitations of these tools. What is it that these tools do especially well, and what they seem to be unable to do? And this is, as in any question that tries to separate the feasible from the infeasible, this is hard. Not only because it's difficult to argue about what is and isn't feasible, but also because the capabilities of these models and tools are evolving very rapidly every day. I'm going to show you an example of a tool that we didn't build, but was built to keep mind. And some of the theorems are able to prove with it in theory. And then spend several minutes at the end talking about the limitations of capabilities that seem to be evident in the work we've done. But this, as I said at the beginning, is a long journey ahead, and we're still not. So let me begin by telling you about the particular tool that we used, and then take it from there. Next, please. Yeah. So the tool that we use, something called Alpha Evolve, and the idea is to evolve programmatic solutions to pieces of tools using language models. Okay. And here's how it works. Right? So the user gets an LLM, a problem we solve, and you'll see the examples we have. Okay. The LLM doesn't come up with a proof. In fact, it doesn't even come up with a piece of the proof. And you'll see in a moment the kinds of pieces of proofs that we're interested in. The LLM comes up with programs, and now here's their Python programs that generate pieces of proofs, okay, or chunks of proofs. Now, next please. Now, these chunks, these programs generate chunks of proofs in a manner you see in a second. And these chunks are scored by some criteria, some artificial criteria that we give the system. Next, please. So what these programs do is print out, generate objects, typically combinatorial objects, that make up some portion of a proof of a theorem. And the generated objects are scored by this criteria with the goal of identifying which programs are more successful in producing the kinds of objects you want. Next, please. Okay, and so what we then is take the more successful programs, and again, not the most successful objects, the more successful program, feed it back into the LLM to generate even more programs with the goal of finding successful objects. Next, please. The programs that don't seem to be doing a good job, we discard. So the weak programs. So again, general idea is start the prompt, tell the LLM what you're looking for. It produces programs that generate these objects that will make up pieces of proofs. Successful pieces, the successful programs are turned back to create new programs. And once the theory is failing, are discarded. Okay, so that's the idea of Alpha Evolve. And this is a tool built around 2 years ago at DeepMind. What I'm next going to do is tell you first set of theorems we're able to prove using Alpha Evolve, and I'll then give you a glimpse of how we did it. Next, please. All right. So the first set of results I want to talk to you about come from the area of hardest approximation. So this is the area of approximation algorithms. And a typical result says that it's unlikely you can approximately solve some problem better than some factor. Okay? So the first problem we looked at was the metric traveling salesman problem. I'm not going to define that. I think everyone in this audience will understand, knows what the TSP is. And the new result derived using alpha is that it is NP harder to approximate the metric traveling salesman problem within a factor better than 111 over 110. Okay, so 111 over 110 is the new world record value for approximating the traffic sales and profit. This improves the long line of results starting with Raghavan case in 1991. And the most recent champion, it's almost a decade old, due to traffic growth obtaining, they obtained a result of 117 over 116. Now, those few were not in this area. We look at squint back and say, okay, that seems like a really tiny improvement. But if you've been working in approximability and hardness, you recognize this is a game of inches. And every step takes a lot of work to get from one constant up to the next one, right? And just for the completeness of your picture, the best one upper bound is just as mentioned below 3 halves. We would call it, and so this is the best known lower bound. It is conjecture, although we talk from proving it, that the correct hardness result is 4/3, but both the upper and the lower bound seem to be far from it. When we get to the next slide, I will tell you how we got here. But let me take a moment to tell you what some of the other results are. So for max 4, we again have a slight improvement on a decade-old result by Austin et al. That says that if you want to approximate the best max 4, getting to better than 98.7% is NPR. In other words, if you have an instance where the best 4 has 5,000, what we're saying is that even getting the 4 to size 987 would be NPR. Okay? And again, you get this feeling of squinting and saying, okay, it's really, that seems like a tiny improvement. But like I said, it's a game of inches. Okay? We also have family of result on approximating max target, similarly max independent set on regular random graphs, 3 regular, 4 regular, etc. And essentially the result is that it's unlikely you can do better than approximation within 5% modulo certain mathematics, certain conjectures. Okay? Just to give you an overview first of how these proofs come about. For the worst case results, we constructed gadget productions, and in particular, AlphaGo was used to construct new gadgets that established these worst case results. For the average case results, we constructed new Ramanujan graphs that plug into a known proof technique, and that yielded these results. Okay? So what I'm going to do next is give you a sense of how these results come about, okay? And the role played by AI in that. I won't go through proofs in detail, okay? But really my goal is to convey to you what is the role that's played by AI, because later in the talk, I will try to give you an argument that it's unlikely we would have gotten these results without the use of AI, without the use of outside help. Okay? Next, please. All right. So here's how the metric TSP proof works. First, this case, the case TSP, it took a lot of manual work, refactoring of prior from collaborators, from work of Prince et al. And others, okay, to get it down to the point where you could see a clean gadget reduction from a problem called hybrid 3 2, which has known hardness approximation. Okay. That we said to AlphaGo, we want you to find a better gadget that will give us a better result, namely 111 over 110. Okay. And so effectively what you're doing is to view the proof of the hardness of metric TSP as a long string. Okay. And the way we formulated the proofs is a gadget, and if we could improve that gadget, we get a better result. And for the purpose of improving that gadget, we said to AlphaGo, we want you to find essentially a graph and weights that optimize some synthetic objective function. And then you plug in this limit graph into the long proofs, you get a new result. Okay? And here, at the bottom of the slide, you see the particular gadget that was found by AlphaGo, surface focus. Okay? I just ask you to note one thing. In this reduction from trillion 2 to TSP, the gadget that we have at the bottom has a certain asymmetry to it, and I want you to note that fact in your head. I'll come back to this briefly towards the end of the talk. Okay. I'm also going to now give you a very quick idea of the corresponding modes for max forecast and for the average case results, so that you get a sense of the kinds of things Alpha Evolve does in pursuit of these theories. Next, please. Okay, great. So the gadget for max forecast turned out to be considerably more complicated to look at than the TSD gadget. So here's the picture, right? So it's a gadget that takes, you know, linear equations, so family of linear equations, what, 3 variables in each equation. It comes up with this 19 node graph. It's got 19 nodes, it's got only edges. The weights vary from 1 to 1,429. Why 1,429? There's no good reason. It's not a particularly interesting number. It's a prime number. But this is what Alpha Evolve came up with in response to a challenge to find a better gadget. So, now, one of the things you should be concerned about at this point is, well, you're telling me this gadget works. Did you actually check it? How do you know if it's correct? Right? And stay tuned for that, because that's a great question, and I'll get to it in short. Next, please. All right. So the atmosphere hardness of max particle and max independence of random graphs. All we did was to take recent work of Kunisky and Liu from Fox 24. And in their proof, they use the family of random of Ramanujan graphs with certain properties. And essentially what we used Alpha Evolve to do was to come up with Ramanujan graphs that were far bigger, therefore gave us much better constants than the original book. We also, using analytical techniques, showed that the lower bounds that we have using Alpha Evolve are essentially the best part. They are not improved. And so in this sense, this is a case where the improvement on the work of Kunisky and Liu has reached essentially the best part thanks to AI. All right, next. So let me take a moment now to talk about this verification work. So on the previous page, previous slide, I showed you the scary gadget with 19 nodes and trained a certain result, max forecast. Why should it be correct, right? And so you have the general problem that the combinatorial logics that are built by Alpha are valid for the training proofs. Okay. Moreover, if you remember the schematic of how Alpha Evolve worked, it is generating these combinatorial logics using programs that are then stored and improved and so on. So the way I want you to think about it is you're going through this loop of improvement in Alpha Evolve thousands and thousands of times, right? And so if verification becomes slow, becomes a major system bottleneck. Right? The PSD gadget we showed you is relatively small. The other ones, the constructions we came up with are far more complex, right? And exhaustive verification, because certainly you can use exhaustive verification of some of these gadgets, could take hours. And if you take hours, then going around thousands of times to solve this work, right? So the solution we hit upon was to use Alpha Evolve itself to write fast verifiers for verifying these gadgets. Okay? And so essentially we instructed it saying, find me a verifier. So we write a Python program that will verify one of these gadgets in under a second. And we pick 1 second as some sort of system constant so that we can go through this like that. And Alpha Evolve came up with verifiers that were some 10,000 times faster than a cluster verification. Okay? Now, how do you know the verifiers that? In general, we don't. Now, we don't know that any of the verifiers that Alpha Evolve came up with was actually in PALM, but not probably right. Okay? So when we finished, and at the end seemed to have results, for instance, the TSD gives a new gadget that is in nuclear. We run an exhaustive verification that takes several hours to make sure that the gadget is indeed valid. And so the claim zero is actually the zero. Okay? So this idea of sloppy verification can be very costly because it lets you go rapidly through the proof evolution process And at the end, you have to do the hard. Next, please. Right. So this thing, start over here. It does outside world doesn't count with LLM standard gadgets. It uses the LLM to evolve code that generates gadgets. Okay. It's a second shot. In the beginning, remember I said it wasn't like a human, the machine are going back and forth with ideas, inspiration. We said, go find this thing. And it came back, not with the hook, but with this chunk, namely the gadget. It does this without understanding what the theorem proves is. It's finding graphs directed by some process going function. Okay. And this inner loop of quick and potentially software verification is powerful. Next, please. Okay. Let me quickly touch on another body of work that we did using AlphaFold. So I'll just remind you, the Ramsey number, given two integers are as small with no arc key or no, as independent set. Okay. How do you find the Ramsey number for given values of R as a certain as in bounds? We will be proving them over the years. But we were interested in these small Ramsey numbers to take property. So you give me two small integers, and I try to tell you what the Ramsey number is. How do you know what the Ramsey number is? In general, you don't. But you can find the lower part solved. Suppose you could find a graph of 35 nodes with no fork peak or 6 independent sets. Then you know the dot force is 336 negative. Yeah. And the next. And so this, no, back here, yeah. So in this case, if you look at the cell in the row marked 4, columns 6, 36 comes by somebody finding such a graph. Right? They found a graph with 35 nodes with no flow peaks, independent sets. Now, the way these things are done is typically computational. So people find a computational technique to generate a graph and then start researching lower bounds. On this table, you see lower bounds, several lower bounds that outside walls found. The actual, in fact, this table is slightly outdated. We've been finding a few more other sets, but let me just focus on explaining what all these numbers and colors are. So the blue set is one where outside wall found a node that cannot be improved. It's the best possible. And in every one of these cases, that tightness was already known. So outside wall matched what is known, and it cannot be improved. A yellow set here says outside wall matched an existing node by finding a graph like the one in this example here, the 35 and 36. But for all these other yellow sets that matched an existing node, it may not have found the exact same node process before. In fact, in many cases, it's a new graphs that we found, or it finds as a graph. Remember that what Alpha is doing is for every one of these sets is generating a program that generates graphs, and it doesn't generate graphs directly. Okay. Now, green set is one where Alpha has found a new lower bound. So this is the new word record. And we have a few more. And so we found this program that generated a graph that establishes your new level. So let's step back and look at what we're doing here. Next, please. All right. So the first thing I want you to know is that every cell in there has very limited T and uses a different approach. It's not like there's one uniform approach. So we looked at all the programs, one for each set that Alpha evolved on, and tried to find some unification. There wasn't it. And indeed, all the prior work also uses bespoke techniques for every set. Okay? But unlike the prior work, in some sense, the meta program, Alpha evolves, is common to all stuff that I showed you in the previous slide. Many cases, natural projects like use some simulated annealing here, scaling graphs here, use cyclic graphs here, etc., with chain together by Alpha evolve. Okay? And indeed, there are results that were known before, that for which we, prior literature did not give program or algorithm that was used. They just said, here's the graph, there's a new load. So in all of these cases, Alpha evolve found an algorithm that is published on GitHub. And in at least one case that I can think of, we now have a new lower bound that surpasses the lower bound that came from an unpublished algorithm. And again, just like you have had sloppy verification, you can use alpha evolve to do fast verification of these things. All right, next. Now I'm going to give you a glimpse of the kind of algorithm that alpha evolve found along the way, right? And this is the algorithm that successfully beat the known lower bounds for R330. Okay, and it's about you start with finding a large base graph, which is a randomized cyclic construction, and we can do some expansion and some simulated deviation at the end, so on, right? So what I want you to understand is that these aren't just simple things someone thought about. These algorithms seem to be fairly sophisticated. What alpha is coming up to beat these lower bounds. Next, please. So I'm going to finish with a few reflections, because, like I said at the beginning, we are early this journey, and it behooves us to reflect on where we are and put in perspective of all the other exciting work that's going on. What are we doing, right? So first, where would these rank among results that we're proud of? Personally, as original results, perhaps fairly low, but to me, what's exciting here is not the what, but the how we went to operate. And is there some inevitable role, unavoidable role for AI? Okay. Music alpha evolve is very syntactic. And I also know that alpha evolve by now is almost 2-year-old technology. So there's not a state. One of the things we've been interested in is what are we learning in this process that leads us to build newer and better tools than alpha evolve. Okay. Next, please. So you could ask, what was AI really needed? Right? Could a talented human use this? Now, it's very hard for me to argue that no talented human that's not with anything. So remember that the famous mathematician Andre Boyle did some of his best work when he was locked up in the prison for 6 months. Right? But it doesn't seem like a human with a simple pencil and paper could have just come up with these things. In the case with TSP, remember I showed you a gadget that had some asymmetry to it. Prior gadgets for the TSP for hardness all had symmetry, so in some sense, we covered some new ground using AlphaGo. But in general, it's going to be difficult to argue that we could have used these results. Right? So only the test of times will tell us whether these results can be equal to surpassed by it. And in at least some cases, previous announcements of AI finding something that were quickly matched or beat by humans. Okay. And so if it stands the test of time, there's some evidence for the need of AI assistance. Next, please. All right. You could also, for contemporary computing, have succeeded, right? Okay, so you used all these deep mind computers, AlphaGo, but maybe some smart person with as much computation, right? And it's hard for me, again, to give you a definite answer. We tried some traditional techniques like batting SMT solvers. The number of constraints in these problems seems to at times go into the 10 to the hundreds, right? And unless you come up with some very ingenious formulation in the language of math programming something, it doesn't seem feasible to just get to it using traditional computation techniques. Now, one of the things that I think about is if you remember the episode of AlphaGo beating Lee Sedol, the human goats champion, in the second game, there was a famous move 37 where experts looked at it and said, wow, we don't think any human would have come up with that. And yeah, it's hard for me to pinpoint such a moment here where a human or well-endowed machine couldn't have come up with these results. But I do think we should dwell on whether the things we're discovering AI are truly beyond humans. And that's not to minimize these results in any way, but it's philosophically a question. And one of the nice reflections in this comes from Alkanan Mossel, his publishes law on in order to say that AI is essential, you should be able to refute that AI is essential. That's the right scientific method to look at this. So that goes. Next, please. Okay. We did try many reasonable types of direct conflict. So you could ask me, why didn't you use stuff like, oh, why not just count the other come up with right? So in many cases, doing that even straight to reconstruct the state of the art. Next, please. All right. One thing is that models are trained in success stories, right? Because mathematicians and data scientists, they've published theorems, and that's what goes into the models. But nobody publishes, well, here's something I tried and didn't work. So in some sense, these searches are best guided by both success and failures. And we need, as a community, to find better ways and gathering models and tools with failure stories so that they can better direct their search with the platform. Next, please. So this is just a recap of what this alpha all seems to be doing, right? This interaction of going through a program that generates these proofs seems to be a powerful paradigm. It's something that we certainly pursue, and we have to understand better with the newer tools we're trying to build. Right? And it leads to questions like, okay, what is the class of theorems that is amenable to such attacks, and what is it? And this goes back to my point at the beginning of trying to find the feasibility boundary in a landscape that's admittedly very fast. Next, please. Finally, I want to point you to a beautiful essay by Bill Thurst from a little over 30 years. And Thurston argues that the mathematician's job isn't just to find proofs or proof theorems, but it's a job to deepen human understanding of mathematics. And by that standard, not all of the work that's coming through AI has this notion of deepening human understanding. Right? We got some little glimpses of insight from certainly from the work that AlphaGo used, but not at the point where you can take some major advance in human understanding of the field, thanks to AlphaGo. I want to finish by a beautiful line from Alan Turing. Yeah, this is fine. So this is the end of his paper where he introduces the imitation game, and he has a penultimate paragraph that reflects on the style of machine learning. That's what we call it today. But then he has this wonderful line at the end. He says, we can only see a short distance ahead, but we can see plenty there that needs to be done. And that's kind of how I feel we are today. There's plenty to be done. A lot of progress to be made. But it's very difficult to look at this 5 to 10 years in the future and say, here's what's going to happen. So this is certainly a very exciting time to be in history. Thank you very much.
Maybe a couple of questions?
Yeah, I'm happy.
All right, then let's thank Prabhakar again.